I want to introduce to you this idea of the quantum mechanical atom and this idea that energy is involved in where the electrons are found within an atom. We're going to scale it down to the subatomic particle level. So we're getting really, really tiny. And we're looking at now individual packets of energy. So the smallest packets of energy that we can measure. And this is the idea of the quantum idea of energy, is that these are small, specific packets of energy. To introduce us to these packets of energy, they really come in this energy called electromagnetic energy. And all electromagnetic energy travels at the speed of light, which is 2.9979 times 10 to the 8th meters per second. So that's incredibly fast. They all have this wave or oscillation that they go through. They act as waves. So they have this fluctuation in intensity for their electrical and magnetic activity. And they have a wide range of different amounts of energy. So you can see on this diagram here, we can go very low frequency, where the wave is really slow and low. This is something that you might see in a radio wave frequency, the frequencies of a lot of cell phones, the either 3G, 5G, whatever the next iteration is going to be, LTE. That's all in this lower radio wavelength. We can move up a little bit more to microwaves, infrared technology. We start to see visible light and ultraviolet light. We start to see this higher energy wave forms here. X-rays and gamma rays are way higher energy. So these can all travel through empty space really fast, and they're really interesting because we can receive this energy through really long and far distances through space. This is how the sun sends the energy to the earth, is through electromagnetic energy. So in order to talk about waves, we have to provide a few different definitions for what they are and some of the properties of those waves. One of those things that we're going to be talking about is the wavelength. And you'll see this symbol called lambda. It's Greek symbol lambda. That is going to represent, anytime you see that, the wavelength. So it's the length of the wave. So the distance between two successive peaks or troughs. So this would be a wavelength, or this would be a wavelength. You can also, in between, you could start at the node, and that would be one wavelength. So that's here's showing you that lambda. This is the length of one wave. Typically, they're found in units of meters, centimeters, nanometers. Visible light, for example, is often given to us in nanometers because it would be about 500 nanometers is going to be about where that visible light spectrum is going to be found. So it just gives us a good unit to work with when we're talking about things in the visible light spectrum. Frequency, this looks like a V, but it's kind of a more fancy V. It's actually the Greek symbol nu. When you see this, this means frequency, and this means the number of waves per second that pass a given point in space. These are often, the units are kind of weird for frequency. It's 1 over seconds, or seconds to the negative first power, which is the same thing. We're also cycles per second. And then the official unit that's more often used is hertz. That unit means per seconds. So if we have this on the left side, we have 2 waves per second. So it's cycles per second. So that would be 2 per second. So this is related by lambda times nu is equal to the speed of light. So if we have the wavelength, for example, we always know the speed of light is going to be 2.99 times 10 to the 8th meters per second. That's a constant. So we can always solve for the nu or the lambda if we have one or the other. A few other properties are, we have amplitude, which is the maximum height and minimum height. So the amplitude is going to be described by how high this peaks. And this is related to the intensity. So if we have more intensity or higher brightness of light, that means the amplitude is higher. It would also be analogous to a stereo system. If we turn up the volume, we're increasing the amplitude. Another point I want to show you are these nodes. These are going to be important when we start talking about electrons acting as waves. These nodes are important parts of where electrons would not be found. There's no amplitude or there's no amount of those at that point. So we'll talk about that when we get there, but this is the place where that waveform goes through the axes. So what does energy have to do with electrons? Well, here's an interesting concept that I want to show you here, and this is the energy diagram for a hydrogen atom. If we have a hydrogen atom that just has one proton in its nucleus, and we are going to give that element some energy through a photon or through electromagnetic radiation, we can increase that level of excitement of the electron. And what you can see here are there are these different shells, and we'll talk about those a little later, but there are different places for energy to go. And one of those things that can happen is it can expand out from the radius of the nucleus where the electron is found. So it can absorb different amounts of energy, and there are only certain packets and spaces that electron can go. And that's where we have that quantization. So it's a specific value. It's not a continuation. It can't go halfway in between one of these lines. It has to be exactly on one of those lines. So it can absorb only a very specific amount of energy to get to those spots there. And once it relaxes, it'll actually be able to relax back to one of those different shells. And when it does relax, that will emit light. So you can see these 4 different spots here. There are 4 different spots that the energy can be. And this is what proves to us this emission, that it's very specific wavelengths of light with specific energy, that they can only be in these 4 different spots to give us these 4 different amounts of energy out. So it corresponds perfectly with that. Again, as we saw earlier, we have electromagnetic spectrum, and there's this idea of different wavelengths and different energies will actually correspond to different amounts of electromagnetic radiation, different colors, as you can see down here, from violet to red, or there can also be involved in X-rays or gamma rays or radio television waves. They're responsible for all of those different types of waves. These are actually coming from different compounds, different atoms that are absorbing certain amounts of energy and then releasing them out as packets of energy or photons or electromagnetic energy that have certain frequencies and wavelengths. So this starts to bring us to the Bohr model of an atom, where this is kind of the first theoretical model of the atom to successfully account for the Rydberg equation. It's not quite perfect. We're going to improve upon this model, but one of the first things that we looked at originally was this idea that we have these different shells and these different spaces. So this kind of helps to understand that, thinking about the protons and the neutrons in the middle, electrons floating around the outside. This is kind of the quintessential idea of an atom that has been universally shown to be how this actually works. We're going to talk about this. This isn't quite true, but it does help to understand and start to explain what is happening in these different steps of energy. As I alluded to earlier, this model starts to fail because the theory doesn't explain what happens if you have more than one electron in an atom, right? A hydrogen's simple. You have a proton, you have an electron, and it's really easy to see what's going on. But there are more complex systems that this doesn't then follow. And we're going to talk about that kind of in the next part of this section, where we start looking more closely at how to explain where electrons are. And we now have to start talking about electrons more as waves and less as particles, because the Bohr model really treats an electron as a particle. But we know from some of the earlier discussion that that's not necessarily true, and that's not necessarily how these things are happening. So it's more complicated than that. The theory also doesn't really explain this idea of the collapsing atom paradox, which means if we have something as simple like we're looking at a proton in the middle and an electron orbiting that proton, it's too simplistic, because what we never see, what we don't see, is an electron ever collapsing into the proton and then kind of fusing together. That doesn't happen because electrons act as waves, and they're going to be in certain places that they're going to not ever be in certain places. We're going to talk about that when we talk about nodes and where we don't find electrons in just a moment here, or in the next section. So we don't see that, and this model doesn't explain why these things don't collapse in on each other. So finally, I want you to kind of think about this. For looking at, for Bohr's atomic theory, when an electron moves from one energy level to another energy level, more distant from the nucleus, which of these following statements is going to be true? So post this in our Blackboard space, and this concludes this part, and then we're going to go into more discussions of electrons and energy and how they change their shape, how they act more like a wave.